Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be covering Chapter 2 for our MCAT General Chemistry playlist, and this chapter is titled The Periodic Table. In this lecture, we're going to cover 4 important objectives. The first objective is titled The Periodic Table. Here we're going to go over a brief history of the periodic table, and we're also going to explain how the modern periodic table is organized. In the second objective, we're going to have a description of the different types of elements. We're going to go over metals, nonmetals, and metalloids. Our third objective is titled Periodic Properties of the Elements. Here, we're going to discuss atomic and ionic radius, ionization energy, electron affinity, electronegativity, and effective nuclear charge. We're going to define each of these terms and go over their periodic table trends. Then last, we're going to move into a discussion on the chemistry of groups. We're going to go over alkali metals, alkaline earth metals, transition metals, chalcogens, halogens, noble gases, and even lanthanides and actinides. Now, before we get started really quickly, a lot of you have been asking for MCAT resource recommendations, and I want to point you to Blueprint. Blueprint, they have customizable study schedules. They have access to all of the AAMC resources, and they even have in-depth exam analytics. In addition, they have both free MCAT resources and they have paid MCAT resources. Now, some of my favorite free resources from Blueprint are the MCAT question of the day, their free equation and mnemonic sheets, and their occasional free live classes. So I highly recommend checking them out. At least take advantage of those free resources they have. With that out of the way, let's go ahead and get started with this first objective. What you see here is a chemist's favorite tool, the periodic table. And we're going to continuously refer to the periodic table in this course, so it's important that we build our knowledge of the periodic table and understand its layout. Where we want to start first here is a little bit of a history lesson. In 1869, the Russian chemist Dmitry Mendeleev, he published the first version of his periodic table of elements. Mendeleev's periodic table, it was revolutionary because it organized the known elements in a way that revealed a pattern of periodically recurring physical and chemical properties when it was arranged according to their atomic weights. Now, this arrangement, it allowed Mendeleev to not only classify elements, but also predict the properties and existence of elements that hadn't been discovered yet. His periodic table essentially left gaps for these unknown elements, and his predictions, they were remarkably accurate, and that really demonstrated the power of his organizational scheme. Now, since then, the periodic table has undergone significant revisions, especially in the earliest 20th century. And this was done by Henry Maslow, and he discovered that the properties of elements are actually better correlated with their atomic number. This is the number of protons in an element's nucleus, rather than organizing it based off of atomic weight like Mendeleev did. Now, this led to the modern periodic law, which states that the chemical and physical properties of elements are a periodic function of their atomic numbers. And by arranging elements by increasing atomic number, the modern periodic table, it corrected inconsistencies that were found in Mendeleev's table, and it definitely provided a more accurate framework for understanding elemental properties. Now, what we see here is the modern periodic table. And the periodic table is now organized into periods, also known as rows, and groups, also known as columns. Now, each period, so this is row, it corresponds to a principal quantum number indicating the energy level of an element's valence electrons. And we have 7, so this is the n equals 1 energy level, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, and n equals 7. Now, if you're wondering about the lanthanides and actinides, technically, these are 2 rows that are placed right here. We just expand on it down here. So technically, these would be inserted right in this part of the periodic table. So what we said was true. All right, we have 7 periods representing the quantum numbers n equals 1 through n equals 7. Now, on that note, moving across a period from left to right, each element has one more proton and one more electron than the preceding element. So you see here, this is carbon, has an atomic number of 6, so it has 6 protons and 6 electrons in its neutral state. The next atom that follows it is nitrogen, and you guessed it, it has one more proton and one more electron, so 7 protons and 7 electrons. Now, this sequential addition of protons and electrons explains the progressive changes in properties that's observed across a period. So, for example, within a single period, elements, they transition from metals on the left to nonmetals here on the right, with metalloids exhibiting intermediate properties. Now, what about groups? All right, groups or columns, so going up and down. Groups, they contain elements that have the same electronic configuration in their valence shell. And what this leads to is similar chemical properties among elements that are in the same group. The elements in a group exhibit similar reactivity. Why? Because they have the same number of valence electrons. And that is what's really crucial in determining how elements interact in chemical reactions. So for example, here we have group 1. All right, we have group 1 right here. These, excluding hydrogen, these elements are known as alkali metals. All of them have one valence electron, and that makes them highly reactive. They want to give up that one valence electron in their outermost shell so that they can reach this full octet, which we're going to discuss later, and that indicates a level of chemical stability. All right, now this group includes lithium, sodium, potassium, and so forth, and their reactivity actually increases down the group as the valence electrons is further from the nucleus and more easily lost in reactions. We're going to elaborate on that in a little bit. Now, in contrast to group 1, we can look at group 18 elements, which are here all the way on the further right side of the periodic table. These elements are known as noble gases, and they have a full valence shell. What that results in is stability, and they are largely unreactive. The stability of noble gases, it arises from their complete valence electron configuration, which makes them unlikely to gain or lose electrons. And this property makes noble gases ideal for applications where non-reactivity is crucial. Now, the periodic table also highlights several important trends, and this is actually the main objective of our third discussion point in this lecture. So in summary, so far, what we know is that the periodic table is a powerful tool that organizes elements based on their atomic number, and doing it this way reveals patterns in their physical and chemical properties. This organization not only reflects the periodic law, but it also provides a really useful framework for being able to predict the behavior of elements and their compounds. And this table structures into periods and groups helps us explain trends that we're going to discuss in our third objective, like atomic and ionic radius, ionization energy, electronegativity, and so forth. Now, with this preliminary understanding of the periodic table in place, we can move into the second objective, which is about the different types of elements. We'll first start by discussing metals. Now, metals are predominantly located on the left side and mostly in the middle of the periodic table. This includes groups like the active metals, so this first group right here, the second group also known as the alkaline earth metals. All of these metals in the middle right here, the transition metals, including lanthanides and actinides, as well as a couple of these elements below the ones with blue dots. So a majority of the periodic table is actually metals. Metals are typically characterized by their shiny appearance. So they have a shiny surface when they're polished, also known as being lustrous. Now, most metals are solids at room temperature. Of course, there's an exception, and that exception is mercury, which is a liquid under standard conditions. Metals also generally exhibit high melting points and densities, although, again, there are some exceptions here. So, for example, lithium actually has a density about half that of water. Now, a key characteristic of metals is their ability to be deformed without breaking. Now, the ability to be deformed into rolls and sheets, all right, that is known as malleability. So malleability refers to the ability of a metal to be hammered or rolled into thin sheets. Now, ductility, this is another important property. It refers to the ability of metals to be drawn into wires. These properties arise from the metallic bonding that's present in metals, where valence electrons are really delocalized and they're free to move throughout this structure. Now, this delocalization of electrons also accounts for another important property of metals, and that is that they are good conductors of heat and electricity. Now, transition metals, these are the ones that are right here in the center. They often have multiple oxidation states, meaning that they can form ions with different charges. This versatility is in forming various oxidation states. This is due to the involvement of d orbital electrons in bonding. Additionally, because the valence electrons in metals are not tightly bound to any one atom and they can move freely, this also plays a role in why metals are such good conductors of heat and electricity. This property also contributes to metals' ability to form positive ions or cations by losing an electron. So for example, iron can exist as Fe3 plus or Fe2 plus depending on the chemical environment. So it could lose 2 or 3 electrons depending on the chemical environment. So in short, metals are good conductors of heat and electricity. They're malleable, ductile, and lustrous, and they tend to lose electrons and become positively charged cations. Now, what about nonmetals? Nonmetals are predominantly found in the upper right side of the periodic table. They're all the metals that are squared off in this brown color on the periodic table. So all of these elements right here and hydrogen are all nonmetals. Now, in contrast to metals, nonmetals are typically brittle in the solid state and they lack any metallic luster. They're usually also very poor conductors of heat and electricity. And these characteristics actually result from the tendency of nonmetals to gain electrons rather than lose them, which makes it difficult for them to conduct electricity. Nonmetals are also more varied in their physical and chemical properties compared to metals. So, for example, carbon, it can exist as graphite, which is a good conductor of electricity, or as a diamond, which is actually an excellent electrical insulator, right? So their properties are a little more varied than metals. Now, we also said, remember, hydrogen is a nonmetal. Let's talk about this because hydrogen is a unique element because despite being a nonmetal, it's actually located in group 1 of the periodic table. This placement is due to hydrogen actually having 1 valence electron in its outermost shell, similar to the rest of the alkali metals here in group 1. However, hydrogen's properties are more akin to those of nonmetals, even though it's placed here. It forms covalent bonds, and it also exists as a diatomic gas at room temperature. Also, hydrogen's ability to form both positive and negative ions further demonstrates its versatile nature, very much setting it apart from the alkali metals. All right, so we talked about metals. Now we've talked about nonmetals. Main takeaways for nonmetals: they're not conductive, not malleable or ductile, not shiny, and they tend to gain electrons and become negatively charged anions. So the complete opposite of metals. Then we have metalloids, or they're also known as semi-metals. And these are elements that exhibit properties intermediate, somewhere between metals and non-metals. They're located along the stair-step line that divides metals and non-metals on the periodic table. These metalloids, they tend to include elements like boron, silicon, germanium, arsenic, antimony, and tellurium. And they're all the elements that have a blue dot on them. All the ones with blue dots on them are metalloids. These elements, they typically have electronegativities and ionization energies that lie somewhere between those of metals and nonmetals. So if we had a spectrum where we had metals on one end and nonmetals on the other end, metalloids would be somewhere in the middle, a blend of both. All right. Now, metalloids, they can also exhibit varying physical properties. They can have a range of densities, a range of melting points and boiling points, and their behavior often depends on the conditions and the elements which they are interacting with. So for example, one of the metalloids is silicon, and this is a well-known metalloid. It has a metallic luster, but it's brittle like a nonmetal. It's a semiconductor, meaning its ability to conduct electricity is better than a nonmetal, but not as good as metals. And this property makes it invaluable in the electronics industry for making components like transistors and diodes. This intermediate properties of metalloids also allow them to act as either metals or nonmetals in chemical reactions, making them extremely useful in a lot of applications. So, in summary, the periodic table categorizes elements into metals, nonmetals, and metalloids based on their physical and chemical properties. Metals are characterized by their malleability, they're ductile, lustrous, and they're great conductors of heat and electricity. Nonmetals are the complete opposites of that, and metalloids, they exhibit a mix of properties from both metals and nonmetals, making them really unique and important in a lot of applications. With that, we're actually ready to begin Objective 3. Here we're going to discuss periodic properties of the elements. To start this section off, we want to establish a foundation by exploring 3 key concepts that influence how valence electrons behave in an atom. Those 3 points deal with effective nuclear charge, the principal quantum number and shielding effect, and then last, the octet rule. So we want to discuss these 3 concepts first before we begin to talk about atomic and ionic radius, electron affinity, electronegativity, and ionization energy and their trends. So we're going to start with the first point on effective nuclear charge. What is that? This is the net positive charge that's experienced by valence electrons in an atom. Now, as we move from left to right across a period on the periodic table, each element, it has one more proton in the nucleus and one more electron. We covered that earlier. Now, this increase in positive charge, it enhances the electrostatic attraction between the protons in the nucleus and the electrons. However, there are inner shell electrons between that outermost electron and the nucleus that kind of shields the outer electrons from experiencing the full charge of the nucleus. And so the effective nuclear charge is essentially the actual nuclear charge, so we can think about it as the number of protons minus the shielding effect of the inner electrons. All right, let me repeat that. That's really important. So if you have valence electrons, outer valence electrons here, all right, they can feel the pull of the protons from the nucleus. However, there are inner electrons that are in the way that partially shield and mitigate this positive attraction between nucleus and outermost valence electron. All right, and that's what we are discussing when we say effective nuclear charge, and we can think about it as essentially the actual nuclear charge, the number of protons, all right, minus the shielding effect of the inner electrons. What does this mean? This means a higher effective nuclear charge pulls the valence electrons closer to the nucleus, and that results in a smaller atomic radius and a more tightly bound electron cloud. We're going to revisit this concept shortly because it does play a significant role in periodic trends. But that second rule that we wanted to talk about as well, all right, now that we've covered effective nuclear charge, the second one has to do with principal quantum number and shielding effect. So as you move down a group on the periodic table, each successive element, it has an additional principal energy level, right? As you move down a group, you go from n equals 1 to n equals 2, all the way down to n equals 7. And as that happens, that means that there's an additional electron shell in the next element as compared to the one above it. These additional inner shells of electrons, they're going to increase the distance between the nucleus and the valence electrons, and that provides more shielding, right? So that if we're looking at a group going down, yada, yada, this element right here, all right, the next following element is going to have an extra outer shell, all right? It's going to have an additional shell. And so that means that outermost electrons are further away from the nucleus as you go down a group, all right? And that increases the distance between the nucleus and the valence electrons, and it provides more shielding. Now, while the nuclear charge increases down a group due to more protons, the effective nuclear charge that's actually felt by the valence electrons, it remains relatively constant because of this shielding effect. The increased distance and shielding result in larger atomic radii down the group because the valence electrons are less tightly bound to the nucleus. Then our third and final point that we want to discuss before we move into periodic trends is the octet rule and chemical stability. The octet rule is a principle that describes the tendency of atoms to gain, lose, or share electrons to achieve a stable electron configuration with 8 valence electrons, similar to that of the noble gases. This configuration, it's energetically favorable, and so it's often associated with chemical stability. However, the octet rule is a guideline rather than a strict rule. There are many exceptions, especially among transition metals and heavier elements, where stable electron configurations can actually have more or fewer than 8 valence electrons. We're going to talk about the octet rule and their exceptions in the following chapter. Now, with these foundational concepts in mind, we can now explore the periodic trends that emerge from the arrangement of elements in the periodic table. And understanding these trends help us predict the properties of elements and their compounds. Of course, to even understand the trends, we're going to first have to define the terminology. All right, then we're going to scroll down to the periodic table and then discuss the trend. And we're going to do that for each category. So we'll first start with discussing atomic radius. We'll define it. All right, we're even going to compare it to ionic radius. And then we're going to scroll to the periodic table and discuss the trend for atomic radius. Then we're going to move on to the next thing, effective nuclear charge. Then the next thing, ionization energy, then electronegativity, and then electron affinity. So that is our workflow here for the next part. We start first with atomic radius. Now, the atomic radius is a term that's used to describe the size of an atom, and it's defined as the average distance from the center of the nucleus to the outermost boundary of the electron cloud. Now, there's a lot to unravel here, actually, because what does it even mean to say the outermost boundary of the electron cloud? So what we're going to do here is we're going to scroll to the next page where we're really going to dive into atomic radius, and we're also going to spend some time with ionic radius. Now, atomic radius, this average distance, is not a fixed physical boundary because electrons, they exist in regions of probability rather than following specific orbital paths. And because electrons are constantly in motion, measuring the atomic radius by examining just a single atom is impractical. Instead, we measure the atomic radius as half the distance between the nuclei of two identical atoms that are briefly in contact with each other. So we take that distance from nucleus to nucleus, and the radius is half that distance. So that's how we practically measure atomic radius. But as for a definition, it is to describe the size of an atom, and it's defined as the average distance from the center of the nucleus to the outermost boundary of the electron cloud. Now, what we want to do next is discuss what are the trends in atomic radius on the periodic table. So we're going to scroll down to our periodic table. All right, what is the trend for atomic radius moving from left to right? As you move from left to right across a period, the atomic radius decreases. All right, and this is due to the increase in the number of protons, which enhances the effective nuclear charge, thereby drawing those electrons closer to the nucleus. So let me help you visualize that, right? As you move across a period, all right, you have lithium. All right, you have lithium that has 3 electrons. So it has those first 2 electrons in that first shell, and then 1 electron in that second shell, right? Because in this period, this is an N equals 2 shell period, right? So lithium has 3 electrons. Then the next atom, beryllium, it has 4 electrons. So it has 2 in that first shell and now 2 in the next shell. And every atom that follows it has an extra electron in the outermost shell, that N equals 2 shell. And so what we're doing here is we're increasing the number of protons as we move across a period, but we're not changing where we're placing the electron in that second shell. All right. And so the increase in the number of protons is just going to enhance the effective nuclear charge. All right, because now we have more protons, but the electrons, the outer electrons, are a similar distance away. All right. Then what's happening is that they're drawing those valence electrons closer to the nucleus, resulting in a decrease in the atomic radius. What about the trend for atomic radius going from bottom to top? Going from bottom to top, the atomic radius decreases as you ascend a group. That's because fewer electron shells are present, which reduces the shielding effect and allows the nucleus to exert a stronger pull on the remaining electron shells. So going from bottom to up, atomic radius decreases. Okay, so that was atomic radius. Second, to contrast atomic radius, we want to talk about ionic radius. Now, while the concept of atomic radius helps us understand the size of neutral atoms, the ionic radius is used to describe the size of charged species or ions. And so the ionic radius is defined as the distance between the nucleus of an ion and the outermost shell of the ion. Now, there are some key differences between the ionic radius of cations versus anions. So that's what we want to discuss here. Cations. All right, when a metal loses 1 or more electrons, it forms a positively charged ion known as a cation. Now, the loss of electrons, it reduces electron-electron repulsions, which allows the remaining electrons to be drawn closer to the nucleus. What does this result in? It results in a smaller radius compared to the neutral atom. All right. So if a cation, all right, if we're losing an electron, if a metal loses an electron, it forms a cation, and the cation is going to have a smaller radius compared to the neutral atom. Additionally, the effective nuclear charge, which is that net positive charge experienced by the electrons, it's going to increase because there's fewer electrons to shield the positive charge of the nucleus, further pulling the electrons inward. And so you can see here, all right, we have group 1, group 2, group 13. You see the neutral atom and then the cation where it has lost an electron. And what you notice is that the ionic radius of the cation is smaller than the radius for the neutral atom, smaller than the atomic radius. So for cations, that is the trend. What about for anions? So when a nonmetal gains one or more electrons, it forms a negatively charged ion known as an anion. Now, the addition of electrons is going to increase electron-electron repulsion. And that causes the electrons to spread out more. This results in a larger radius compared to the neutral atom. All right, so if we're looking, for example, at group 16 or group 17, here you have oxygen, here you have an oxygen anion where it's gained 2 electrons. Notice the ionic radius, all right, is greater than the radius for the neutral atom, the atomic radius for the neutral atom. So for anions, when you gain electrons, the ionic radius is larger compared to the radius for the neutral atom. And here the effective nuclear charge on each electron, it decreases as there are more electrons being pulled by the same number of protons, resulting in that more diffuse electron cloud, hence the larger ionic radius. All right, so to keep in mind for trends in ionic radius, all right, it really follows some specific trends for metals versus nonmetals versus metalloids. So for metals, if you're looking at the periodic table for metals, which are located, like we said, on the left side and in the middle of the periodic table, metals tend to lose electrons to form cations. All right, so for example, sodium loses 1 electron to form sodium plus, and magnesium loses 2 electrons to form magnesium 2 plus. As these metals lose electrons, the resulting cations have smaller radii than their neutral atoms. So that's the trend for metals. What about nonmetals? Nonmetals are found on the right side of the periodic table over here, and they tend to gain electrons to form anions. As nonmetals gain electrons, the resulting anions have larger radii than their neutral atoms. Can't forget the metalloids. All right, they're located in that stair-step line dividing metals and nonmetals. They can behave either as metals or nonmetals depending on the context. So they're a little more complicated to know the trends for. All right, but the main takeaways is understanding the trends in ionic radius specifically for metals versus non-metals. With that, all right, let's move into discussing. We're going to go back up to our table. All right, we've made it past atomic radius. We even had a discussion on ionic radius. Let's move on to effective nuclear charge. All right, this is going to be a refresher because we already talked about it, but effective nuclear charge is the actual amount of positive charge that's experienced by an electron in a multi-electron atom. It is the charge that's felt by an electron when both the actual nuclear charge, all right, and the repulsive effects of other electrons are considered. And this concept is really important for understanding periodic trends like atomic size and ionization energy. And it's quantified as the nuclear charge, or the number of protons, minus the shielding effect due to the inner shell electrons. So you can kind of, in a very oversimplified manner, think of it as like number of protons minus number of inner core electrons. All right, now with that refresher and definition for effective nuclear charge, let us go straight to our periodic table and discuss the trends in effective nuclear charge. So the question is, first and foremost, what is the trend for effective nuclear charge going from the left all the way to the right? Effective nuclear charge is going to increase. As you move across a period, the number of protons in the nucleus increases, leading to a higher nuclear charge. And since additional electrons are added to the same energy level and do not significantly increase shielding, the positive charge felt by the valence electrons increases as you move from left to right, resulting in a higher effective nuclear charge. What about going from bottom to top? All right, bottom to top, what happens with effective nuclear charge? It also increases when moving up a group. Moving up a group, electrons are in lower energy levels closer to the nucleus. So these inner electrons are more effective at shielding the outer electrons, making the outer electrons feel a stronger pull from the nucleus. And so this results in an increased effective nuclear charge for those valence electrons. So going from bottom to top, effective nuclear charge increases. All right, let's go back and focus on ionization energy now. Ionization energy, this is the energy that is required to remove an electron from a gaseous atom or ion. Now, this process is going to be endothermic. You're removing an electron, which means you need to absorb energy to overcome the attraction between that negatively charged electron and positively charged nucleus to be able to remove it. Ionization energy is a key indicator of an element's reactivity, and it's very much influenced also by atomic radius and effective nuclear charge. Now, the energy required to remove the first electron, that's called the first ionization energy. The energy that's required to remove a second electron is called the second ionization energy. Now, elements in groups 1 and 2, like lithium and beryllium, they have low ionization energies and thereby are known as active metals. These metals are actually always found in compounds because they don't exist naturally in their neutral forms. In addition, ionization energy is really important because you can determine a lot by the degree of ionization energy, that first, second, third, so on. The first ionization energy will always be smaller than the second ionization energy, which will always be smaller than the third. However, that degree to which the ionization energy increases provides clues about the identity of the atoms. So, for example, if losing a certain number of electrons gives an element noble gas-like configuration, then you know that removing that subsequent electron is going to cost way more energy. All right, it's going to cost much more energy. So, with all that information in mind, let's go back to the periodic table now and discuss the trends in ionization energy. So going from left to right, what is the trend for ionization energy? Ionization energy is going to increase. The electrons are held more tightly as you go from left to right by the stronger effective nuclear charge, thus actually requiring more energy to be able to remove an electron. What about going from bottom to top? Ionization energy increases moving upward. There are fewer electron shells that are present, and so the electrons are held closer to the nucleus, and so that increases the energy needed to ionize them. All right, so going from left to right, ionization energy increases. Going from bottom to top, ionization energy also increases. Now we can move into electronegativity. This is a really important concept, especially as we move into the next chapter where we talk about ionic and covalent bonding. Electronegativity, this is a measure of an atom's ability to attract and retain shared electrons in a chemical bond. It's a dimensionless quantity often described on the Pauling scale. And while memorizing electronegativity values for a couple of key elements like carbon, oxygen, hydrogen, nitrogen can be useful, understanding the periodic trends will actually enable you to make some really good educated deductions about the relative electronegativities of elements. Now, electronegativity, it's influenced by an element's atomic number and also the distance that its valence electrons reside from the nucleus. Higher atomic numbers and shorter distances between the nucleus and valence electrons results in higher electronegativity. So let's take, for example, in a covalent bond between hydrogen and chlorine, chlorine exhibits a higher electronegativity, all right, indicating that it has a stronger affinity for the shared electron pair. All right, it's going to pull the electron slightly more towards it since it's more electronegative. And this differential in electronegativity is really pivotal in determining the polarity of the bond and the overall chemical behavior of molecules. It also results in a partial negative charge for the chlorine, since it pulls the electrons a little bit more towards it, and it results in a partial positive charge on the hydrogen. Now, in addition, I want to point that electronegativity and ionization energy are really related. Elements with high electronegativity typically have high ionization energies because both properties depend on the effective nuclear charge and the distance of valence electrons from the nucleus. However, there's an exception. The first three noble gases, helium, neon, and argon, are exceptions. They have high ionization energies, but they actually have negligible electronegativity because they don't tend to form bonds. So those are three exceptions you should commit to memory. Now we go back to the periodic table, and our focus is on the trend for electronegativity. All right, so our question here is, what is the trend in electronegativity going from left to right? Electronegativity increases due to the greater effective nuclear charge as you move from left to right, and this allows atoms to attract bonding electrons more strongly. All right, what about going from bottom to top? What's the trend for electronegativity? It increases from bottom to top because atoms higher up in a group have fewer electron shells, resulting in a stronger attraction between the nucleus and the valence electrons. Now, with that, we're able to move on to our last and final concept, and that is electron affinity. Electron affinity is the measure of the energy change when an electron is actually added to a neutral atom, forming a negative ion. All right, so it's the opposite of ionization energy. Ionization energy was energy required to remove an electron. Electron affinity is energy required to add an electron. It's a key descriptor of an atom's likelihood to accept an electron and thus form anions. And this is actually going to be an exothermic process. So it expels energy in the form of heat, and again, very much the opposite of ionization energy. Now, the stronger the electrostatic pull, the higher the effective nuclear charge between the nucleus and the valence electrons. All right, the greater the energy release will be when the atom actually gains the electron. So taking that information, let's see how it translates into periodic table trend. What is the trend for electron affinity as we move from left to right? It's going to increase. This means that atoms are more likely to accept an additional electron. And this trend is because the atomic nucleus becomes more positively charged due to the addition of protons, which is going to increase the effective nuclear charge, but without a proportional increase in shielding effect, since the additional electrons are being added to the same energy level. And so as a result, the added electron feels a stronger attraction to the nucleus. What about going from bottom to top? Electron affinity increases going from bottom to top as the valence shell gets closer to the nucleus. And what you notice is a lot of the explanation for these different trends really falls back on effective nuclear charge. So understanding effective nuclear charge allows us to also reason what the trends may be if we don't remember them. So if there's anything to remember, it's effective nuclear charge, the definition and the trends, and you'll be able to deduce the rest of the trends for these concepts based off of that understanding. That's why we discussed it first and foremost before we even got into defining atomic radius, ionization energy, electronegativity, and electron affinity. Now with that, to end this chapter, let's move into our fourth and final objective and discuss the different groups on the periodic table and some of their unique properties. Here, we're going to discuss alkali metals, alkaline earth metals, transition metals, chalcogens, halogens, noble gases, lanthanides, and actinides. So let's go ahead and get started. We're going to first start with alkali metals, which are this group 1 elements, excluding hydrogen. Now, alkali metals, they possess most of the classical physical properties of metals, except their densities are lower than those of other metals. The alkali metals also have one loosely bound electron in their outermost shell, and they'll typically take on an oxidation state of +1 because they prefer to lose an electron to achieve a noble gas-like configuration. Now, they, along with the alkaline earth metals, are the most reactive of all metals. In addition, the alkali metals, their effective nuclear charge is very low, giving them the largest atomic radii of all the elements in their respective periods. Alkali metals, again, highly reactive, especially with water, forming hydroxides and releasing hydrogen gas. They're stored under oil to prevent reactions with moisture in the air. Common alkali metals include lithium, sodium, and potassium. Now, what about alkaline earth metals? They're group 2 metals here. They also possess many properties that are characteristic of metals. They share similarities with the alkali metals, but they have slightly higher effective nuclear charges and thus slightly smaller atomic radii. Now, they take on an oxidation state of +2, and so they can lose 2 electrons to achieve noble gas-like configurations. In addition, alkaline earth metals are also highly reactive, though a little less than the alkali metals, and they also react with water to form hydroxides, though not as vigorously as group 1 elements. All right, common alkaline earth metals include magnesium and calcium. What about our chalcogens? These are a group that include both metals and nonmetals, very crucial for normal biological functions. They each have 6 electrons in their valence shell, and due to their proximity to the metalloids, they generally have small atomic radii and larger ionic radii. Now, they can also take on oxidation states of -2 or +6, depending on whether they are nonmetals or metals, respectively. This group includes essential elements for life like oxygen and sulfur. Oxygen is necessary for respiration in many organisms, while sulfur is a key component in amino acids and proteins. Now, halogens, this is group 17. Halogens are highly reactive nonmetals with 7 valence electrons. These elements are super eager to gain 1 electron to complete their octets and achieve a noble gas-like configuration. Halogens, therefore, typically take on an oxidation state of -1. They also have the highest electronegativities, and they also have high electron affinities, making them very reactive, especially toward the alkali metals and the alkaline earth metals. Halogens also form salts when they react with metals like sodium chloride, for example. Common halogens include fluorine, chlorine, bromine, and iodine. Then here in group 18, we have our noble gases. They have fully filled valence shells in their standard state, and they prefer not to give up or take on additional electrons. They have very high ionization energies, and for helium, neon, and argon, they have virtually non-existent electronegativities and electron affinities. Noble gases, again, are known for their lack of reactivity due to their stable electronic configuration. They're used in a lot of applications. They're used in lighting, like neon lights, and in inert environments for chemical reactions, argon in welding, for example. Then we have our transition metals. They're groups 3 through 12 here. They're characterized by their ability to form multiple oxidation states, which allow them to form colorful complexes with nonmetals in solution. They have low electron affinities, low ionization energies, and low electronegativities. And these metals, they are typically hard, and they have high melting points and boiling points. Transition metals very much play crucial roles in biological systems. So, for example, iron is essential for oxygen transport and hemoglobin, and copper is a key component in various enzymes. They're also really important in industrial applications like catalysts in chemical reactions and in the production of things like alloys. So that's our transition metals. Now we also have these 2 lonely rows here at the bottom, right? They would essentially go right here, but they're usually written at the bottom. Lanthanides and actinides. Now, actinides are very radioactive. Lanthanides, except for one, are not radioactive, and they're extremely useful. They are used in a lot of modern technology. They're in electronics, in your laptops, your phones. They're also used in wind turbines and medical imaging tools like MRIs. And the cool thing is they're very much earth abundant, but the mining, purification, separation process for lanthanides is extremely complicated. It uses a lot of solvents that are environmentally detrimental, and the process is extremely energy intensive. And actually, a lot of my work in my PhD deals with looking for biologically inspired ligands for lanthanide separation to kind of help that process. And so, yeah, that's my work. Just a little blurb right there. But with that, we've covered all our main groups here. All right. Each of these groups on the periodic table exhibits unique properties that are influenced by their electron configurations and their positions in the periodic table. And so understanding these groups, understanding the trends that we covered so far, really helps us predict the behavior of elements and their compounds in chemical reactions and in applications. And with that, I hope that this lecture has been helpful. Let me know if you have any questions, comments, concerns down below. Again, go check out Blueprint for some of their free MCAT resources. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.